All right, so thanks everyone for attending or watching. Today I'm going to show some experimental results from two projects. So the title of this presentation is Measuring Healing and Failure in Experiments on Clay-Bearing Fault Gouges. And so these two sets of experiments will focus on clay gouges and looking at both these two processes, sort of frictional healing and then what happens during an earthquake. So the reason I'm focusing on clays is because clays are really common and they're influential minerals in fault gouges. They are found especially in more mature faults. So clays are forming from hydration or other weathering reactions in most rock types, so both felsic and mafic rocks at these more shallow crustal levels. So I've got some just nice photos of examples here from some major faults that I'm sure people recognize. So some very clay-rich Seyfod core, this core from the JFAS drilling expedition in the Japan Trench, some other drill core from the Alpine Fault in New Zealand, this outcrop photo of the Mugi Melange in Japan, which is very illite rich subduction interface there, and the Carbonaris Fault out in Spain. And so these materials are really common in fault gouges, so presumably they're going to contribute to the mechanical properties of faults. And so we know that they do. So we care about them because they are known to affect these mechanical properties, most notably things like frictional strength and rate and state parameters, as well as the permeability of fault zones. And this is in part due to, in the one hand here, this little cartoon of their clay structure. So we have these sheets of atoms here with OH or water-filled sites between them, and this really strong basal plane alignment, or these really sort of very anisotropic basal planes with this weak bonding between those planes are imparting this inherent weakness. And in addition to that, on this zoom in SEM photo here, we can see the really platy and flaky nature of these silicates. And so this can also contribute to really fast alignment of those basal planes in fault gouges and the formation of really strong deformation fabrics. And so these kind of inherent properties influence, like I said, the strength or permeability of fault zones, and that's been measured in a ton of studies. So this is just one simple example of friction coefficient, and we can see that amongst a bunch of different clay species, you have very low friction coefficients of sort of 0.1 to 0.4. And there are a lot of other studies as well looking at rate and state friction of clay-rich gouges, but there are relatively few studies that look at how clays are impacting frictional healing or how clays are responding to earthquake ruptures. So those are two of the topics I'm going to focus on here. So like I said, the main question of this talk is how clay content is influencing fault behavior during healing and earthquakes, these sort of two different sections of the seismic cycle. And in the first section, I'll show friction experiments on synthetic mixtures of quartz and clay, looking specifically at slide-hold slide tests to measure their healing rates. In the second part, I'll look at the fracture energy of clay-bearing sediments from the Cascadia subduction zone and thinking about how fracture energy might tell us something about the dynamic rupture through the shallow subduction zone. Okay. So first of all, why is frictional healing an important process? So healing is fundamental in the seismic cycle because it's what allowed the fault to heal and re-strengthen between earthquakes. So as you can see in this sort of nice cartoon, we have fault strength indicated here in pink. And so as shear stress on the fault increases from tectonic loading, once that intersects with the fault strength, you get an earthquake and the strength drops. And this recovery of strength here in between earthquakes is what we're talking about and what we're focusing on. And that's going to be a really fundamental part of allowing the next earthquake to occur. And we can also see how the rate of healing also can influence earthquake properties, things like earthquake size or the recurrence interval. So for example, in this plot of repeating earthquakes from the Calaveras Fault in the San Andreas system, we see that larger stress drop faults have occurred after a longer recurrence interval between earthquakes, which is a direct observation suggesting that the fault is strengthening during the interseismic period and allowing it to reach these larger stress drops. In a more recent observation of healing has also been used to explain slow slip in the shallow subduction environment. So for this example, it comes from the Hukarangi subduction zone, where fault gouges with near zero healing rates, so that's kind of represented by these blue dots here, and this dashed line, these near zero healing rates are coinciding with almost negligible stress drops, the really tiny stress drops, and that are corresponding with these slow slip events on the Hukarangi subduction zone. So that is another sort of potential importance of frictional healing and how it might inform our understanding of seismicity on these major faults. So what is frictional healing, or how do we get frictional healing? Healing is this time-dependent increase in frictional strength, and that can be achieved either by increasing the contact quality or the strength of the contacts, or the contact quantity, or the total area of the real contact of the fault. So shown here in this classic example from Dietrich and Kilgore, we see that the contact area represented by these bright patches in this material is increasing with the elapsed time. So going from these kind of red cores and growing out from these patches as the fault is held in contact for a longer time. And these increases in either contact quality or quantity are driven by a variety of mechanisms, things like adhesion, interfacial bonding, compaction, low temperature plasticity, or the creep at asperity contacts, and pressure solution. So these are all sort of interplaying at possibly different time scales or different spatial scales as well. And how might we expect for the clay content to affect some of these mechanisms? So for example, adhesion between quartz could be reduced by just the reduction in the number of quartz-quartz contacts. You might also expect that compaction will become sort of cut off or less effective after a time due to the saturation of the contact area from the alignment of clay minerals. Or it's also been shown that clay content can increase pressure solution rates in sort of clay quartz mixtures. So how might that might also play a role. And so what we did was do a bunch of these friction experiments on quartz and smectite mixtures. Smectite is one of these clay species, really common, especially as a weathering product from mafic rocks. So it's common in subduction zones. And this is actually a new analysis of experiments that were originally reported in this paper here. And so in this publication, they published the sort of rate and state parameters from these experiments, but never really looked at the healing parts of the experiments. So we're doing a new analysis here. So these experiments were conducted in a biaxial apparatus like this, where a normal load was applied horizontally on these two sets of sliding blocks with the sample in between here and here. And then shear load was applied from the top, driving the center block down, causing slip on these two planes. And then displacement transducers were used to measure the position of the ram here and measure this sort of external shear displacement of that central block. And then we also have a transducer that is measuring the thickness of the gouge here. So we can see how it evolves during the test. These experiments were conducted at room temperature and room humidity, and again on these synthetic mixtures of quartz and smectite with up to 100% smectite. All right, so the mechanical data from these tests looks like this. So we have a series of rate steps here. So sort of these squiggles are the rate steps, and then a series of slide, hold, slide tests in the middle here, and another series of rate steps. And so what we're going to focus in on are these slide, hold, slides. So during a slide, hold, slide test, so this is a zoom in of in time versus a sort of apparent friction coefficient here. So during the slide, hold, slide test, we have established some steady state friction coefficient by sliding up to this point. We stop the advance of that shear load ram and allow the stress in the fault to decay until we again reload the sample and start shearing again. You reach a peak sort of after resliding friction here, and then it decays back to a sort of steady state value. And so what we're measuring each time is the length of this hold, the amount of peak stress after the hold, and the amount of sort of decay in strength that also occurs during the hold. So the data for that looks like this, where with increasing hold time, you have increasing both peak shear stress and this creep relaxation is what we're going to call it, or stress relaxation. And then for each set of these slides for each experiment, we're fitting this evolution with this equation here to get the healing rate or stress relaxation rate beta or beta C, as you'll see it be noted. And from just this, we can already see the reduction in friction coefficient with increasing clay content. So on this plot here, the most quartz-rich sample here, 90% quartz, is the strongest with that sort of 0.6, 0.65 friction coefficient. And as we introduce more and more clay, we reduce down to a friction coefficient of around 0.2 to 0.3. And as well, we see the total amount of that healing or the stress relaxation reduces as we increase the clay content as well. So now translating those into these rates, so beta or beta C for healing and stress relaxation rates, we see a very clear reduction in both of these rates with clay content here. And then if we add on some more measurements from natural samples with similar compositions, so this is a bunch of previous data from either synthetic end members or other natural samples with similar sort of quartz and or clay content. Those seem to overlap with our data, which suggests that this is a consistent effect of the clay content itself. And then what we also are curious about is how this coincides with some other frictional properties. So if we look at how beta corresponds with the steady state frictional strength, we can see that these quartz-rich gouges here are heal the most and are also the strongest. And so that's sort of a consistent effect between our data and the natural samples from previous experiments. And this also seems to correspond with the A-B parameters. So this is a rate and state parameter that's sort of a measure of the frictional stability, where positive A-B is leads to more stable sliding behavior, and negative A-B is a condition for unstable or seismic slip. And we see also here that with increasing clay content, you get more stable A-B parameters associated with those low healing rates. And in the opposite, you get in the quartz-rich samples, you get more velocity neutral or velocity weakening or unstable properties with these high healing rates in the quartz-rich gouges. So it seems like these parameters are not evolving separately from one another. They're sort of co-varying. So as healing rate changes, it is corresponding with changes in the frictional strength and possibly the stability. But I do want to note that A-B in these rate and state parameters is dependent on a lot of other factors and can, is a little more tenuous maybe than this relationship with just frictional strength. I just want to note that there. So then if we want to think about what might be controlling or what might be the primary mechanism of healing in these experiments. So we plot here, we have that, again, this change in strength, change in frictional strength during the hold. We're healing here, and that's plotted against the change in thickness of the sample, and then the change in shear displacement during the hold as well. And what we can see is a very clear correlation between the amount of healing and the amount of sort of thickness change during the hold. So this is suggesting that most of the healing here is associated with compaction and shear creep, or possibly most likely shear enhanced compaction as well, which is increasing the contact area during these holds and leading to this greater healing in the quartz-rich samples. So that gives us a model of something like this, where if you compare your quartz-rich sample to a clay-bearing sample, this as compaction, as the sample compacts during the hold, you get, in the quartz-rich samples, you get this sort of classical increase of contact area with time as the quartz particles come together. While in the clay-rich sample, you saturate your contact area really quickly. So as the clay fabric forms and you align all these individual clay minerals, the clay-clay contacts are not able to grow in contact area the same way that the quartz contacts are because of that alignment and that platy shape. So you end up saturating the contact area and limiting the amount of healing you're able to achieve. You're also reducing just the number of quartz contacts. So any of the mechanisms that apply to quartz contacts, such as the adhesion or interfacial bonding that can be really strong in quartz, even under just room humidity. If you remove that by increasing the amount of clay, you're also sort of limiting the amount of healing you might expect to see. So we thought maybe it would be fun to test this idea by trying to capture the change in healing as the fabric develops. So this, you can see in our mechanical data, this really marked difference in the shape of the stress strain curve here from having a straight peak to flat, just steady state value in the quartz-rich contacts. Quartz-rich sample versus the more clay-rich sample, where you have this marked peak strength here, and then it sort of decays to a steady state value. And this shape is really has been linked to fabric formation in previous studies. So, for example, in this set of experiments, they did repeat tests where they measured the fabric strength at each point here, and showed that the fabric strength is indeed evolving with increasing shear strain here, associated with this change in shape and change in frictional strength. And this has also been shown in these experiments here. So this is a set of experiments on very similar materials of quartz-smectite mixtures, where and I really apologize for the inverse color scheme here. So in this case, the blue samples are the low smectite samples. So here with increased clay content well, I'll start with, in each experiment, as you increase, as you are deforming the sample, you get this same sort of peak in shear stress down to a lower value. So as you're loading up the sample, you reach a peak friction, and with increasing strain, you're reducing the friction coefficient. And this is corresponding with the change in permeability that is tracking the strength of the fabric. So with the more clay-rich samples, you get a stronger decrease, a lower permeability that's corresponding to an increased clay fabric. And so we wanted to see if we could measure the change in healing rate associated with this fabric formation, but we don't have any of the slide-hold-slide tests in these regions. So all the slide-hold-slide tests are in the middle of the experiment here, when a steady state value has already been reached. So we wanted to try, because the B parameter of A minus B in rate and state friction is related to the healing rate beta. So this is just for our experiments here, but you can see that they're very closely related and are just about even the same value in most cases. We wanted to see if we could track changes in the B parameter during these rate steps as the test is evolving and presumably the fabric is forming. So we looked to see if we could see this change. So this is the evolution of B with shear displacement through that first section of rate steps for all the samples. And so initially, maybe not, maybe it's not sensitive enough. It doesn't really seem to be much of anything here. So for the quartz-rich samples, we might not expect to see a big change because we don't observe that sort of peak to steady state frictional change. So this isn't that surprising. But then for the clay-rich samples, it also sort of looks like there isn't much of a trend. But if I were try to pick out something with trends within these examples, these two, sort of the 50 and 70% smectite samples, seem to have the most evidence of maybe a decrease in the beta parameter with increasing fabric development. And this might be related to the fact that these two samples are also the ones that have the most gradual changes in the peak to steady state values. But, it's not as satisfying as we might have hoped, but, it's still kind of interesting. And still suggests that this idea of the clay fabric formation and the saturation of contact area is what's giving us this massively reduced healing rate in the clay-rich samples. All right, so just sort of sum up from just this section here. So this is a little schematic cartoon of this competition, again, between the tectonic loading rate and the healing rate. So for example, something with a really high healing rate, something with a more quartz-rich gouge, similar to what's been observed in the Calaveras fault zone. You have a really high healing rate here, and that is in stark contrast to the really low healing rate here, similar to what's been observed for the San Andreas fault gouges. And so with this change of healing rate with increasing clay content going from high healing to low healing, you can already see how this might be affecting the earthquake cycle here. So if this intersection here sort of gives you maximum recurrence interval or an expected possible recurrence interval for an earthquake, and this axis here is giving you the maximum stress drop, you can see that there might be you might expect to see a difference between maybe larger events or the potential for larger events and longer recurrence intervals in stronger and higher healing gouges versus the combination of low healing rates and low frictional strength in clay-rich gouges favoring these more frequent and smaller earthquakes. So then we also wanted to, this is more of a work in progress, also just sort of a fun, small start of a research project here. So we also wondered how healing might change through the seismic cycles. So we already know, and Jod Bedford previously in this seminar series talked a lot about how healing can occur really quickly right after earthquakes by some sort of more like atom to atom chemical bonding mechanisms. And then we know that in our experiments, this compaction process is sort of on an intermediate time scale. So how might the healing rate itself sort of change during different parts of the seismic cycle? So in this, these are some results from a previous paper from Carrie Ryan that showed that the amount of total healing here, this is decreasing with the stress on the sample during the hold. So this parameter here is an indication of the stress during the hold relative to the stress right before the hold or the stress during that sort of steady state sliding. And so if you go from keeping the stress near that initial stress here, you get much less healing than if you reduce it to nearly zero or have almost no stress on the fault during the hold. So that's sort of increase. You can imagine how that might play into the seismic cycle where the stress in the fault is evolving with tectonic loading and really affecting the amount of healing that you get through the seismic cycle. So we conducted another set of experiments. So this is a small benchtop triaxial vessel where we were sort of messing around with a new sample assembly here. So this is a double direct triaxial setup. So you put gouge powder in these two interfaces here between the central block and these side pieces, and that goes in the vessel here. And so you can either control the setup during the hold by holding a constant oil pressure in this chamber. So that would be one of these stress controlled tests where you're setting the stress to either be some percentage of the initial value or what have you, or you can do the more traditional displacement controlled holds where you're just holding the load piston here fixed during the hold and letting the stress evolve during the tests like the ones I showed you in the previous section. So in these tests, we're also running at just room temperature and room humidity, and these are just experiments on quartz powders initially. So this is a really new project, so we only have these sort of two preliminary results. So I'll walk through these a little bit. So here we have, again, this is the log hold time and the amount of healing here. And so what you can see is we did a series of holds in both the displacement controlled traditional test way and these stress controlled tests. So in this case, we did 60% of that initial stress value. On this side, we did 35% of that initial value. And in the two tests, you can see that in agreement with Carrie's results, we get higher total healing with the stress controlled holds. So as if the stress is lower, you get more healing. However, the rate, Carrie's results didn't report the rate of healing, right? So if you look at the rate, this beta here and here, we see that the beta is actually higher in the displacement controlled tests for this experiment, and then it's actually lower in this experiment. So this is still kind of a work in progress, but interesting to think about how the healing rate might be affected by changing stress through the seismic cycle. So coming back to this again and just summing up some of the ideas about this work in progress, again, so on these shorter time scales, healing is controlled by faster acting mechanisms like water absorption or compaction in our experiments, or low temperature plasticity. And on longer time scales, especially time scales of the seismic cycle, and as the stress is changing on the fault, building up or relaxing, mechanisms like pressure solution might also be more important in this intervening time scale. So this is an ongoing project, and interesting to see what more will come out of that in the future. So now getting on to the failure part. So, what happens once you intersect this line and you get an earthquake? So I think we all know why we care about earthquakes, but they, as we know, especially the large ones, can be really damaging and societally important. And in this particular example of the 2011 Tohoku Oki earthquake, there was significant damage because of one unusual aspect about this particular earthquake. So in this event, they had larger than expected amount of slip on the really shallow subduction interface here, up to, I think, maybe 50 or 60 meters of slip on the shallowest portion, which is not what's typical. Normally, you'd expect the slip to be concentrated in the center of the earthquake patch. But in this case, this really shallow, large slip also contributed to generating a really large tsunami with that event. And so we know that at the Cascadia subduction zone here in North America, it has a really long history of really large earthquakes. And so this is just a sort of timeline of all the large events and how much of the trench they spanned. So you can see lots of magnitude 9 equivalent type events inferred from this record, the seismological paleoseismic record here for the Cascadia subduction zone. So since we haven't had an event in 300 years, but given this history, a large magnitude earthquake is somewhat inevitable at Cascadia, how might we expect the shallow sediments here to respond? So would we also expect to see a really large shallow slip, something like the Tohoku Oki earthquake that could generate a tsunami, or might we not expect something like that? And so one of the interpretations made for the Tohoku Oki earthquake is that the sediments along that part of the plate boundary had really low fracture energy. So fracture energy can be a proxy for the ability of the earthquake to propagate through a material, and fracture energy is just one of these components of the earthquake energy budget as well. So if the total energy represented here by this kind of gray polygon, fracture energy is this segment here, and it's added up with the radiated energy this is fracture energy. This is the radiated energy and the frictional work to add up to the total earthquake energy budget. And so this bit of the triangle is representing how hard it is for the earthquake to propagate. And so some previous work inferred that the really low fracture energy of the sediments along the plate boundary there contributed to the large shallow slip during that event. So what we wanted to do is take some samples from the Cascadia subduction zone and run a similar test and see how these sediments respond. So we took 3 representative samples from the input section at Cascadia. So 2 of our samples are coming from this site 888 and 1 from site 1027. And the importance of site 1027 here is that this is more likely the material where that will be localizing the décollement within the deformation zone here. So these 3 samples are from 30 to 55% clay. Most of that clay is also smectite and illite. And we sort of have these 3 lithologies that are representative of this input section here, with most of the interest, in my case, being focused on this mudstone sample here. So we deform these samples in this high velocity rotary shear machine here. This is located at the Kochi Core Center in Japan. So in this rotational vessel here, you have a top piston that is stationary and a bottom piston that will rotate. And you put your sample between 2 rings in here, and you can apply a normal load and measure the permeability. However, some of these samples were so impermeable that the initial test broke the machine because the permeability wasn't reading correctly, and we applied too much normal load. So we unfortunately don't actually have permeability measurements for these experiments, but alas. We ran these at 2 to 8 megapascals of normal load, just at room temperature and room humidity again. And we spun the sample up to 1 meter per second, or sort of those co-seismic slip speeds. And all these experiments were done with water applied to the sample as well. Right, so the mechanical data from these experiments looks like this, where shear stress is plotted as this solid black line against slip, and the slip rate is plotted here as this dashed line. So in each test, we accelerate up to 1 meter per second and then decelerate. And as we accelerate, the slip achieves some peak stress and then decays due to a dynamic weakening process. And then we can fit a model to that stress decay that looks something like this, where we get out this slip weakening distance here, and then the area under the curve between the stress evolution and this slip weakening distance is the fracture energy. So we did this model to fit each experiment, and the data looks something like this. So for each of these lithologies at each of these normal stresses, you have the stress drop, which is that difference between the peak stress and the sort of steady state, or like the dynamic stress out here, is increasing as we increase normal stress. That slip weakening distance, the distance at which it's decayed some set amount, is decreasing with normal stress. So that triangle is sort of getting shorter and taller as we're increasing normal stress, and that results in the fracture energy itself not really changing. So one of the reasons we might be interested in how this is changing with normal stress is thinking about how we might be able to apply our results to sort of those shallow depths. So most of these high velocity machines are sort of limited in the amount of normal stress they can apply. So we want to think about how we can extrapolate these results to more realistic depths at subduction zones. So in this case, it seems like the fracture energy is not really changing with normal stress, which might suggest that we could sort of rely on this value to be representative of what might be applicable throughout that sort of shallow zone where these sediments are existing. And we don't really see a lot of variation either with the lithology here. So that 30 to 55% clay range is not really imparting any significant change on the fracture energy. We also did a series of these similar tests on a bunch of different clay species. So we tested these 5 species that are all really common in fault gouges, or talc being more common, sort of deeper in the earth. And we didn't really see much of a difference either. I mean, you could pick apart a few things in here, but they seem to all behave really similar to one another, with maybe some noticeable differences in their friction coefficients. But overall, you get under dry conditions, they sort of have a higher fracture energy than they do under wet conditions, where it's a little bit more of a cloud here as well. So now when we take our results and these results and compile them with a bunch of data from the literature, we see we categorized all the data into these 3 different types. So all the experiments from my paper either went into this wet gouge category, so that's the wet experiments on the clay species, as well as the Cascadia gouge experiments, and then these this category for dry gouges. So these are just clay-rich gouges deformed under dry conditions. And the color scale here is corresponding to clay content from 0 to 100% clay. And then this sort of orange to red color scale is for intact rocks. So here, this is just different rock types rather than a compositional change. That's more like 0 to 100%. These are just 5 different rock types. And so what we see is a really similar trend across all these categories, where you have the stress drop is increasing with normal stress, slip weakening distance is decreasing, and you get sort of these consistent fracture energy numbers that are sort of flat across normal stress space. And from here, we can see that The wet gouges are by far the lowest fracture energy materials, with the dry gouges sort of hanging out at the top of their range, and the intact rocks up to at least an order of magnitude larger in fracture energy than any of the gouges themselves. And so then we wanted to compare, okay, so if each of these sort of fracture energies are sort of consistent across these different experimental conditions, we wanted to think then about how Cascadia might compare with other subduction zones. So if we plot all the available data for experiments conducted on subduction zone materials here, we have the Cascadia gouges are here with a fracture energy of around 0.1 to 1. And then I would focus on the wet data here because most subduction zones have water presence. That's going to be what's most relevant. So for a bunch of different subduction zones here, including JFAST, which is the material, again, from the plate boundary zone where the Tohoku Oki earthquake is most likely to be something similar to that. We can see that there's a huge difference in the fracture energy here of up to a couple orders of magnitude between these Cascadia samples and these other subduction materials. So Cascadia has a relatively high fracture energy, and this might actually give us a lower risk of this larger than predicted shallow slip at Cascadia in the event of the next kind of big earthquake. All right, so just wrapping up some of the key takeaways here. So how did clay content influence the fault rupture behavior and or fault behavior during healing and earthquake rupture? So saw in frictional healing that clay-bearing gouges heal much more slowly than quartz gouges, and these low healing rates combine with low frictional strength to favor more frequent and smaller earthquakes. And then in the second part, the fracture energy of all wet gouges is relatively low compared to other types of materials, and the higher fracture energy of these Cascadia sediments could inhibit this larger than predicted shallow slip scenario for the Cascadia subductions. All right, so that's all I've got, and please ask questions.